Hi, I'm Ned, and I make games. Would you like to start writing shaders, but don't know where to begin? Or are you having issues with URP's shader graph and would like an alternative? In this tutorial series, I'll walk you through writing a fully featured general-purpose shader for Unity's Universal Render Pipeline, exclusively in code. This topic is pretty big, so I'll break it into several videos. Check the video description for links to each tutorial and a playlist too. We'll start with understanding the structure of shaders, and then move on to lighting and shadows, before finishing with more advanced topics like physically based materials and custom lighting models. Also, if you prefer reading tutorials, I've created a written version of the entire series, also linked in the video description. Before I move on, I want to thank all my patrons for helping make this series possible, and give a big shout out to my next-gen patron, Krooby-Dooby-Doo. Thank you all so much. I'd like to quickly show off a wonderful game from some long-time viewers, Kitty Cat Squash. It's an adorable, casual puzzle game where you match cute kitties and try to beat your high scores. It starts simple but can quickly become a brain teaser. Try out a bunch of different game modes, Gravity was my favorite, and unlock 16 different cats. I love seeing Juliet on my board, so precious. Kitty Cat Squash is available on Steam, the Google Play Store, and the Amazon App Store. Go get your cute kitty fix! Thank you Inspired by Madness Games for sponsoring this video. Let's lay out some goals of this tutorial series. My aim is to teach how to write shaders. I will show several examples, writing each step by step and explaining as we go. Do not view these examples as ready for production shaders, but rather as a blueprint that you can customize to your game's needs. After completing this series, you'll know how to write your own version of URP's standard lit shader, as well as customize it with your own lighting algorithm and more. You'll also know several optimization techniques and how to leverage Unity's debugging tools to diagnose and fix rendering bugs. The examples in this tutorial were tested in Unity 2020.3 and 2021.3. As you follow the tutorial, you will come across many features that are only possible in 2021. However, I have written the shaders so that the same code runs in each version. There's quite a lot to set up and understand before anything will display on screen, which can make learning shaders pretty difficult. To speed up the process, I'll explain information as needed, and I might gloss over some edge cases or technicalities. Don't worry, I'll address them if they become important later on. To keep this series from becoming even longer, I will assume that you have some general game development knowledge. You should be comfortable using Unity and its 3D game tools, such as models, textures, materials, and mesh renderers. And although you need no prior experience writing shaders, you should know how to program. C# experience will definitely be useful. With all that out of the way, let's get started. In this series, we'll use Unity's Universal Render Pipeline. It's one of several rendering frameworks that Unity provides, but I chose URP for this project due to its recency and ability to support a wide variety of platforms, all while remaining pretty lightweight. I would highly suggest creating a fresh project for this tutorial. You can either select the URP project template, or use a blank template. Add URP manually through the package manager and activate it in graphics settings. Either way, create a new standard scene to work with. Large shaders, like the one we'll write, are made of several files. To help keep things organized, create a new folder called MyLit to contain them all. Create a shader file by selecting Unlit Shader from the Create dialog and name it mylit.shader. If you create a material, you'll already see your shader in the shader selection menu of the Material Inspector. It will be under the Unlit submenu. Open your shader file in your code editor of choice. If you're using Visual Studio, sometimes Unity doesn't generate a Visual Studio project correctly when there are no C# scripts present. First, create an empty C# script, so your shader will appear in the Solution Explorer. Regardless, inside mylit.shader is a lot of automatically generated code. Delete it all for now. This part of a shader is written in a language called ShaderLab, and it defines meta information about the actual drawing code. The first line opens a shader block and defines the shader's name in the material inspector. Any slashes will create subsections in the selection menu, useful for organization. The block is bound by curly braces, like classes in C#. A shader is more than just code that draws. A single shader is actually made of many, sometimes thousands of smaller functions. Unity can choose to run any of them depending on the situation. They're organized into several subdivisions, the topmost of which are known as subshaders. Subshaders allow you to write different code for different render pipelines, and Unity will automatically pick the correct subshader to use at any time. Define a subshader with the subshader block, and then add a tags block to set the render pipeline. Tags blocks hold user-defined metadata in a format sort of like a C# dictionary. Tell Unity to use this subshader when the universal rendering pipeline is active by setting the render pipeline tag to universal pipeline. That's the only subshader that we'll ever need in this tutorial. Subshaders are just the first subdivision of a shader. Below them are passes. Passes' purpose is a bit more abstract. Each pass has a specific job to help draw the entire scene, like calculating lighting, casting shadows, or creating special data for post-processing effects. Unity expects all shaders to have specific passes to enable all of URP's features, but for now, let's only focus on the most important pass, the one that draws a material's color. To signal that this pass will draw color, add a tags block inside. The pass type key is light mode, and the value for a lit color pass is universal forward. You can also name passes, which will help a lot in debugging. Okay, we're almost ready to write some code. URP shader code is written in a language called HLSL, which is similar to a streamlined C++. To mark a section of a shader file as containing HLSL, surround it with the HLSL program and end HLSL code words. To keep things organized, I like to keep HLSL code in a separate file from the .shader metadata. Thankfully, this is easy to do. You can't create an HLSL file directly in Unity, but you can in Visual Studio or inside your file system. Either way, name this new file mylitForwardLitPass.HLSL. and open it in your code editor. I just want to mention that many code editors don't work well with URP shaders. So while working through this tutorial, ignore any errors that you see in your code editor and just rely on Unity's console. When writing shaders, you need to have a different mindset than you would when working with C#. For one, there's no heap, meaning most variables work like numeric primitives or structs. You can't define classes or methods or use inheritance. Structs and functions are still available to help you organize your code. If you've ever worked with data-driven design, you'll also feel at home writing shaders. The focus is gathering data and then transforming it from one form to another. In the broadest sense, shaders transform meshes, materials, and orientation data into colors on the screen. There are two standard functions which the system calls, kind of like the start and update functions in monobehaviors. These functions are called the Vertex and Fragment functions, and every pass must have one of each. These both focus on transforming data from one form to another. The Vertex function takes mesh and world position data and transforms it into positions on the screen. The Fragment function takes those positions as well as material settings and produces pixel colors. Unity's rendering system employs something called the graphics pipeline to link together these functions and handle low-level logic. The pipeline gathers and prepares your data, calls the Vertex and Fragment functions, and displays the final colors on the screen. It's made of several stages, running one after another, kind of like an assembly line. Each stage has a specific job, transforming data for later down in the assembly line. There are two special stages, the Vertex and Fragment stages, which are programmable. They run the Vertex and Fragment functions that you write. The other stages are not programmable and run the same code for all shaders, although you can influence them with various settings. Let's take a look at each stage, starting at the beginning, the input assembler. It prepares data for the Vertex stage, gathering data from meshes and packaging it in a neat struct. Structs in HLSL are very similar to C#, a pass-by value variable containing various data fields. This struct is customizable, and you can choose what data the input assembler gathers by adding fields to the struct. But just what kind of data can the input assembler access? The input assembler works with meshes, specifically mesh vertices. Each vertex has a bunch of data assigned to it, such as position, normal vector, texture UVs, etc. Each data type is known as a vertex data stream. To access any stream in your input structure, you simply need to tag it and the assembler will automatically set it for you. For example, here's an input struct for our forward passes vertex function. It defines a struct called attributes, which has a field called position, with a type called float3. Float3 is the HLSL term for C# vector3, or a vector containing 3 float numbers. We can use semantics to tag variables, and the input assembler will automatically set them to a particular data stream. For example, the position semantic corresponds to vertex position. Keep in mind that only the semantic determines what data the input assembler will choose to place in variables. Feel free to name variables however you wish. We'll see more semantics later on. HLSL uses them pretty often to help the graphics pipeline along. With that, let's move on to the Vertex stage. As a programmable stage, you get to define the code that runs here. Defining a function in HLSL is very similar to C#, with a return type, void at the moment, a function name, and a list of arguments. An argument's type precedes the variable name. This function only needs a single argument of attributes type. The Vertex stage's primary objective is to compute where mesh vertices appear on the screen. However, notice that the attribute struct only contains a single position, only data for a single vertex. The render pipeline actually calls the Vertex function multiple times, passing it data for each vertex until all are placed on the screen. In fact, many calls will run in parallel. If you've ever programmed multi-threaded systems, you know that parallel processing can introduce a lot of complexity. Shaders bypass a lot of this by forbidding storage of state information. Each Vertex function call is effectively isolated from all the others. You cannot pass the result of one Vertex function, or any data computed inside, to another. Each call can only depend on the data in the input struct, as well as other global data, but more on that later. In addition, each Vertex function call only knows about data of a single vertex. This is mostly for efficiency. The GPU doesn't want to load the entire mesh at once. We need to compute the screen position for a vertex described in the attribute struct. When talking about positions, it's important to determine the coordinate system that it's defined in, its space. The position vertex data stream gives values in object space, which is another name for the local space that you're accustomed to in Unity's scene editor. If you view a mesh in a 3D modeling program, these positions are also displayed there. Another space you'll often use is world space. It's a common space that all objects exist in relative to one another. To get world space from object space, just apply an object's transform component. Unity provides this data to shaders, as we'll see soon. However, a vertex's position on screen is described using a space called clip space. An explanation of clip space would fill an entire tutorial, but luckily we don't have to work with it directly. URP provides a nice function to convert an object space position to clip space. To access it, we first need to access the URP shaders library. In HLSL, we can reference any other HLSL file with the #include directive. These commands tell the shader processor to read the file located at a given location and copy its contents into this line. If you're curious what's inside the lighting.hLSL file, or any other URP source file, you can read them yourself in your packages folder. Included files can themselves include many other files, leading to a kind of tree structure. For instance, lighting HLSL will pull in many helpful functions from across the entire URP library. One such function, getVertexPositionInputs, is located in the shader variable functions.hLSL file. Its source code isn't really important, but it returns a structure containing the past object space position converted into various other spaces. Clip space is one of them, just what we need. Note that clip space is a float4 type. If you tried to store it in a float3, Unity would give you a warning that data will be truncated or lost. This is a common source of bugs, so always heed these warnings and use the correct vector size. Keeping track of which space a position is in can get tricky pretty fast. Standard URP code adds a suffix to all position variables indicating the space. OS denotes object space, CS clip space, etc. We should follow this pattern as well. Next, we must fulfill the vertex stage's job and output the clip space position for the input vertex. To do that, let's define another struct called Interpolators to serve as the vertex stage's return type. Write a float4 position CS field inside of it with the SV_position semantic. The semantic signals that this field contains clip space vertex positions. Have the vertex function return an interpolator struct, declare a variable of interpolator's type, set the position CS field, and return the structure. With that, the vertex stage is complete. The next stage in the rendering pipeline is called the Rasterizer. The Rasterizer takes all vertex screen positions and calculates which of the mesh's triangles appear over which pixels on the screen. If a triangle is entirely off screen, the render is smart enough to ignore it. The Rasterizer then gathers all data for the next stage in the pipeline, the Fragment Stage. The Fragment Stage is also programmable, and the Fragment function runs once for every pixel the Rasterizer determines contains a triangle. The Fragment function calculates and outputs the final color each pixel should display, but of course, each call only handles one pixel. The Fragment function has a form like this. It takes a struct as an argument, which contains data output from the Vertex function. Naturally, the type should match, so both should be an interpolator. The values inside input have been modified by the Rasterizer. For instance, position CS no longer contains clip space position, but rather this fragment's pixel position. You can also pass other data from the Vertex function into the Fragment function through the interpolator struct, a technique that we'll use later on. The Fragment function outputs a float4, the color of the pixel. It might be strange to think about, but colors are just vectors. They contain a red, green, blue, and alpha value, each ranging from 0 to 1. To let the pipeline know that we're returning the final pixel color, tag the entire Fragment function with the SV_target semantic. When tagging a function with a semantic, the compiler interprets the return value as having that semantic. So we can finally display something on screen now. Let's just color all pixels white. Return a float4 with all components set to 1. See here that you don't need to write new in HLSL when constructing vectors, just the type name is fine. The last stage in the graphics pipeline is the presentation stage. It takes the output of the Fragment function and, together with information from the Rasterizer, colors all pixels accordingly. There's one last thing to do. We need to register our vertex and fragment functions to a shader pass. Return to the mylit.shader file. Tell the compiler to read the code inside your mylit forward_litpass.HLSL file using a #include command. Next, register the vertex and fragment functions using a #pragma command. #pragma has a variety of uses relating to shader metadata, but the vertex and fragment subcommands register the corresponding functions to the containing pass. Make sure that the function names match those in your HLSL file. And we're now finally ready to view your shader. Make sure the material has mylit selected and create a sphere in your scene. Give it your material. It should now appear as a flat white circle. If it's colored magenta or there's some other issue, check Unity's console and the shader asset to see if there are any errors. Okay, so we have a flat white circle now. That's a good starting place. Let's make the color adjustable from the Material Inspector. This is possible through a system Unity calls Material Properties. Material properties are essentially HLSL variables that can be set and edited through the Material Inspector in Unity. They are specified per material and allow objects using the same shader to look different. If you are wondering what's the difference between a shader and a material, this is basically it. A material is a shader with specific property settings. We can define properties inside the .shader file with a properties block. The syntax for these is inconsistent, but I'll explain it. To define a color property, first decide on a reference name. This is how you'll access the property in HLSL. By convention, property names start with an underscore. Follow that with a parentheses pair, like you're writing a function. The first argument is a string. This is a label, how it will display in the material inspector. The next argument is the property type. There are various, but color defines a color property. Close the parentheses and then set a default value. The syntax is different for each property type, but for colors, start with an equal sign and then the red, green, blue alpha values inside of parentheses. As mentioned before, colors are just 4 float values, each corresponding to a color channel: red, green, blue, and alpha. These combine to create any color that a computer can display. Each number ranges from 0 to 1, where white is all 1s and black is all 0s. For alpha, 1 is opaque and 0 is invisible. If you'd like more info on how these numbers combine to create a color, I have a link in the video description. Now you should be able to see your property in the material inspector. Later, this shader will have many properties, so we should organize them. Add a header label denoting surface options. To do that, use this header command. Strangely, the label is not enclosed in quotation marks here. There's one last thing that we should do. Properties can be tagged with attributes, like classes in C#. These give properties special features. Tag color tint with the main color attribute. Now it's possible to easily set this property from C# using material.color. The property is all set up, but the value is not reflected on screen. Open mylit forward-lit-pass.HLSL. Although we defined a property in ShaderLab, we must also define it here in HLSL. Make sure the reference name matches exactly. Unity will automatically synchronize this variable with the material inspector. Earlier, I did say that vertex and fragment functions could only access data from a single vertex or fragment, and while this is true, they can also access any material properties. These variables are uniform, meaning they don't change while the pipeline is running. Unity sets them before the pipeline begins, and you cannot modify them from a vertex or fragment function. With this in mind, have the fragment function return color tint as the final color. Return to the scene editor, select your material, and change the color tint property. The shader should immediately reflect your choice. Flat colors are great, but it'd be really cool to vary the color across the sphere. We can do this with textures. Shaders love working with textures. They're just image files, but shaders think of them as 2D arrays of color data. When you zoom into a texture, this does become pretty obvious. To add a texture to a shader, first add a texture material property. Defining a texture property is much the same as a color property. Instead of listing a type as color, set it to 2D. The syntax for default textures is kind of strange. Following the equal sign, type white with quotes, followed by a pair of curly braces. If no texture is set in the material inspector, Unity will fill this property with a small white texture by default. You can also set the default color to black, gray, or red. Similarly to the main color attribute, there's also a main texture attribute. Tagging this property makes it easily assignable from C# using material.mainTexture. Your property should now show up in the material inspector. Notice the 4 numbers beside it. They allow you to set an offset and scale for this texture, which is useful for tiling. Now let's take a look at the HLSL side of things. Defining a texture variable is a bit more complicated than a color variable. You first must use this special syntax to define a 2D texture. Once again, the name must match the property reference exactly. Texture 2D here is not a type, but something called a macro. You can think of macros similarly to functions, except they run on the text making up code. You can create macros yourself using the #define command. Before compiling, the system will search for any text matching a defined macro and replace the macro name with the text that you specify. Macros can also have arguments. The system will replace any occurrences of argument names in the macro definition with whatever text that you pass in. This is a really simple overview of macros, but they can be pretty useful in shader code. HLSL doesn't have inheritance or polymorphism, so if you want to work with any structure that has a position OS field, but you don't necessarily know the structure type, a macro can do the trick. Here's an example. They're also great at handling platform differences, which is what Unity has done with Texture 2D. See, different graphics APIs like DirectX, OpenGL, etc. use different type names for textures. To make shader code platform independent, Unity provides a variety of macros to deal with textures. That's just one less thing that we have to worry about. Moving on, there are a couple more variables that Unity automatically sets when you define a texture property. Textures have a companion structure called a sampler, which defines how to read a texture. Options include the sampling and clamping mode that you're familiar with from the texture importer, point, bilinear, etc. Unity stores samplers in a second variable, which you define with the sampler macro. The name here is important. It must always have the pattern sampler followed by the texture reference name. Finally, remember the tiling and offset values from the material inspector? Unity stores those inside of a float4 variable. The name must follow the pattern of the texture name followed by st. Inside, the x and y component hold the x and y scales, while the z and w components hold the x and y offsets. And yes, the fourth component of a float4 vector is referred to as w in HLSL. Now we'd like to sample the texture or read color data from it. We should do that in the Fragment stage to apply texture colors to each pixel. Use the sample texture 2D macro to get the color out of a texture at a specific location. It takes 3 arguments, the texture, the sampler, and the UV coordinate to sample. Well, what are UVs? UVs are texture coordinates assigned to all vertices of a mesh, which define how a texture wraps around a model. Think of how cartographers try to unwrap a globe to fit on a flat map. They're basically assigning UVs to positions on the globe. UVs are float2 variables, where the x and y coordinates define a 2D position on a texture. UVs are normalized or independent of the texture's dimensions. They always range from 0 to 1, and by convention, 0, 0 is the bottom left corner of a texture. Unfortunately, we can't grab UVs out of thin air in the Fragment stage. They're another vertex data stream that the input assembler needs to gather. Add a float2 UV field to the attribute structure with a textcoord 0 semantic. Textcoord 0 is short for texture coordinate set number 0. Models can have many sets of UVs or texture coordinates. For instance, Unity uses textcoord 1 for lightmap UVs, but we'll get to that later. The attribute struct is not available in the Vertex stage either. However, we can store data in the Interpolator struct, which will eventually make its way to the Fragment stage. Add another float2 UV field there. Have it also use the textcoord 0 semantic. In the Vertex function, pass the UV from the attribute struct to the Interpolator struct. We can also apply UV scaling and offset there, which we might as well. This way we'll only have to compute it once per vertex instead of once per pixel. It's a good idea to do as much as possible in the Vertex function since it generally runs fewer times than the Fragment function. Unity provides the transform text macro to apply tiling. There are 2 interesting things about it. First, the double hash tells the precompiler to append text to whatever is passed in as the macro argument. When the macro runs, you can see how it replaces name with _colormap, correctly referencing colormap st. Second, the x, y, and zw suffixes give easy access to a pair of components as a float2. This mechanism is called swizzling. You can ask for any combination of the x, y, z, and w components in any order. The compiler will construct an appropriately sized float vector variable for you. You can also use R, G, B, and A the same way, which is more intuitive for colors. It's even possible to assign values with a swizzle operator. Anyway, now we have the UV data in the Fragment stage, but let's take a moment to really think about what's happening here. The Vertex function outputs data for each vertex. The Rasterizer takes those values, places the vertices on the screen, and figures out what pixels cover the formed triangle. It finally generates an input structure for each fragment function call, but what value will input UV have for each fragment? The Rasterizer will interpolate any field tagged with a textcoord semantic using an algorithm called barycentric interpolation. You're probably familiar with linear interpolation, where a value on a number line is expressed as the weighted average of the values at each endpoint. Barycentric interpolation uses the same idea, except extends it to a triangle. The value at any point inside the triangle is a weighted average of the values at each corner. Luckily, the Rasterizer handles all of this for us, so the algorithm is not really important. To recap, the values in interpolators are a combination of values returned by the Vertex function. Specifically, for any fragment, they are a combination of values from the 3 vertices forming the triangle that covers this fragment's pixel. Well, all that for some UVs, but we finally have all that we need to call sample texture 2D. It returns a float for the color of the texture at the specified UV position, depending on the sampler's sample mode, point, bilinear, etc. This color may be a combination of adjacent pixels to help smooth things out. Regardless, multiply the sample with the color tint property and then return it. In HLSL, multiplying 2 vectors is a component-wise operation, meaning the x components of each vector are multiplied together, then the y components, etc. All arithmetic operators work like this. In the scene editor, set a texture on your material and marvel at what you've accomplished. Note how the texture and color tint properties interact. Also, notice that if your texture has an alpha component, the shader doesn't really handle transparency yet, so the sphere will always be opaque. We'll fix that in a future tutorial, so stay tuned. I hope that this whet your appetite for shader programming, because we're really just getting started. In the next part of this tutorial series, we'll add simple lighting to finally give objects dimensionality, and then we'll delve into shadows, learning how to add additional passes to a shader. You've gotten past a lot of the theory and can now focus on the fun stuff. Please stay tuned and subscribe and press the bell to be notified when my next tutorial video goes live. If you enjoyed this, consider liking the video as well. It really helps out with the YouTube algorithm. If you have any issues or questions, please feel free to leave a comment or contact me on any of my social media accounts. I want to take another moment to thank all of my patrons for helping make this video possible and give a big shout out to my next gen patron, Krooby-Dooby-Doo. Again, thank you all for your support. It really does mean a lot. And if you want to download an example shader from this tutorial or any of my others, you can join my Patreon as well. And finally, don't forget to check out Kitty Cat Squash. Thanks again, Inspired by Madness Games, for sponsoring this video. Everyone, thanks so much again for watching, and make games.